Have you ever wondered what you are made of? If you could zoom in, past your skin, past your cells, what would you find? For thousands of years, people have asked this very question. The ancient Greeks imagined tiny, indivisible particles they called atomos, which means uncuttable. For a long time, this was just an idea, a philosophical guess. But science is not about guessing, it is about finding out. This is the story of how we peered into the heart of matter itself. It is a journey of discovery, a timeline that takes us from a simple, solid ball to a universe of swirling, energetic particles. Our guide on this journey will be the scientific method. Ask a question, do an experiment, see where the evidence leads. It all started with a bright idea and some very thin gold foil. In 1909, a physicist from New Zealand named Ernest Rutherford wanted to test the Plum Pudding model of the atom. His experiment was, in principle, quite simple. He decided to shoot tiny, positively charged particles, alpha particles, at a sheet of gold foil only a few thousand atoms thick. Think of it like throwing baseballs at a thin sheet of tissue paper. The Plum Pudding model said the positive charge was spread out, so the alpha particles should pass straight through with only minor deflections. Rutherford assigned the experiment to his assistants, Hans Geiger, Ernest Marsden. For weeks they sat in a darkened room watching for faint flashes on a detector screen. Most particles flew straight through the foil, but Rutherford asked them to move the detector to look for large-angle scattering. It was a long shot, just in case. What they found next would change physics forever. Rutherford later said it was like firing a 15-inch shell at tissue paper and it coming back to hit you. Out of many thousands of alpha particles, about 1 in 8,000 did not go through. Rutherford's model was a triumph, but it had a fatal flaw. According to the laws of classical physics, the orbiting electrons should have been in big trouble. An orbiting charged particle, like an electron, should constantly radiate energy. As it lost energy, its orbit would decay and it would spiral inward, crashing into the nucleus in a fraction of a second. If this were true, every atom in the universe would instantly collapse. But they do not. The world is stable, our desks, our chairs, we ourselves. Something was wrong with the model, or with the laws of physics as they were understood. The solution came in 1913 from a young Danish physicist, Niels Bohr. Bohr dared to suggest something revolutionary. He proposed the old rules of physics did not apply inside the atom. He introduced ideas from the new world of quantum theory. Electrons could not orbit at just any distance. They were restricted to specific, fixed orbits, energy levels. Much like planets, but with a crucial difference. In these special orbits, an electron did not radiate energy. The atom was stable. Bohr's model was like a ladder. An electron could stand on one rung or another, never in between. It could jump up by absorbing energy and jump down by emitting light, with color matching the energy difference. This explained atomic spectra and worked brilliantly for hydrogen, bridging theory and experiment, but failed for complex atoms and finer details. A deeper, stranger theory was needed. The problems with the Bohr model hinted that something was fundamentally strange about the subatomic world. The next great leap in understanding was a shift called quantum mechanics. In the mid-1920s, Werner Heisenberg, Erwin Schrödinger, they proposed a radical new way to describe electrons. Stop thinking of electrons as tiny balls orbiting like planets. An electron behaves as a particle. An electron behaves as a wave. This wave-particle duality lies at the heart of quantum strangeness. In 1927, Heisenberg formulated the uncertainty principle, a fundamental limit to how precisely we can know certain pairs of properties at once. For an electron, we can never know its exact position and exact momentum at the same time. The more precisely we measure one, the less we know the other. This is not instrument error. It is a property of nature. That idea destroys the neat, predictable orbits of Bohr's model. Schrödinger answered with a powerful equation whose solution gives a wave function, a probability map. Instead of a fixed orbit, the electron exists in a probability cloud or orbital with high and low probability regions, like a blurry time-lapse of motion. The quantum model explained complex spectra, chemical bonds, and much more. The cloud is a map of likelihood, less definite than orbits, far more accurate, underpinning modern chemistry and physics. While quantum mechanics revolutionized electrons, another mystery was brewing at the heart of the atom, the nucleus. Rutherford had shown the nucleus was small, dense, and positively charged. The simplest nucleus, hydrogen, a single positively charged particle. This particle was named the proton in 1920. Scientists realized the number of protons determined the element, the atomic number. An atom with 1 proton is hydrogen, with 2 is helium, with 6 is carbon, and so on. But atomic mass was often much higher than protons alone could explain. Helium about 4 times hydrogen, carbon about 12 times. There was extra mass in the nucleus with no charge. Rutherford speculated about a neutral particle, but finding it was incredibly difficult. Without charge, it would not be deflected by fields and would pass through matter like a ghost. Extremely hard to detect. The breakthrough finally came in 1932. James Chadwick studied a strange radiation from beryllium bombarded with alpha particles. It was highly penetrating and could knock protons out of paraffin wax. Chadwick performed careful experiments and calculations. He concluded it was a stream of uncharged particles with mass similar to the proton. He had discovered the neutron, revealing a nucleus of protons and neutrons packed tightly together. With the discovery of the proton, neutron, electron, the picture seemed complete and tidy. But science rarely stands still. To probe deeper, physicists needed more powerful tools to smash particles with far higher energies. This need gave rise to particle accelerators, using powerful electric and magnetic fields to accelerate particles to nearly the speed of light, then slam them into targets or each other. Collisions convert motion into matter, E equals mc squared. A host of new exotic particles appeared, often unstable and short-lived. In the 50s and 60s, as accelerators grew, the count exploded. It was like opening a closet and having hundreds of unknown objects tumble out. Physicists found particles called pions, kaons, lambdas, sigmas, and many, many more. It became the particle zoo. Were all of these fundamental? It seemed unlikely. Nature prefers simplicity. Patterns began to emerge like a new periodic table. Particles were grouped by mass, charge, spin. Complexity hinted at a simpler, deeper layer. It was an invitation to look further. As physicists sorted the particle zoo, tantalizing patterns appeared. They organized particles into families using mathematics. But classification is not explanation. Like classifying animals before understanding genetics and evolution. In 1964, Murray Gell-Mann and George Zweig independently proposed a bold, elegant solution. Many particles, including the proton and neutron, were composite. They were made of smaller constituents. Gell-Mann named them quarks, from James Joyce. 3 quarks for muster mark, initially up-down strange. Each quark carried fractional electric charge, 2, 3, or 1, 3. A proton, 2 up quarks and 1 down quark. Add psu 3, 1, 3, psu 1. A neutron, 1 up and 2 down. Add plus 2 to 3, 1 door 3, 1 door 3, 0. Other particles are quark and antiquark combinations, order from chaos. For years it was seen as a model. No isolated quark had been seen. Late 1960s, early 1970s at SLAC provided direct evidence. Electrons scattered off hard, point-like objects. The quarks were real. Quark conformation led to the Standard Model. Our best description of fundamental particles and forces tested with incredible precision. It is the modern inventory of the universe's basic ingredients. Everything we see is built from 2 families, quarks and leptons. Quarks are the building blocks of protons and neutrons. There are 6 flavors: up, down, charm, strange, top, bottom. Up and down make ordinary matter. The others are heavier, short-lived, born in high-energy collisions. The other family is leptons, electron, muon, tau, and their neutrinos. 6 in total. That is it for matter. 12 particles build everything. Forces are carried by particles called bosons. There are 4 fundamental forces. Electromagnetism is carried by the photon. The weak nuclear force is carried by the W and Z bosons. The strong nuclear force binds quarks via gluons. Quantum chromodynamics explains confinement. Like a rubber band, pulling quarks apart creates new quarks. They remain confined. Our journey from Rutherford's gold foil to the elegant Standard Model shows how profoundly our view of the atom has changed. We started with a simple planetary system and ended with a complex dance of quarks, leptons, and force-carrying bosons under quantum rules. Each step was driven by experiment that did not fit current theory, forcing deeper, more complete ideas. Questioning, testing, revising, the engine of progress. The Standard Model stands as a monumental achievement, its predictions confirmed to astounding precision. From a single electron to the proton's interior, applications transformed our lives. MRI, PET scans, the World Wide Web, semiconductors. Yet it is not the final word, an incomplete story. It does not include gravity, nor explain dark matter or dark energy, nor why 6 quarks and 6 leptons have the masses they do. This is not a failure. It is science's strength. Physicists worldwide push boundaries, searching for phenomena beyond the Standard Model, from supersymmetry to extra dimensions and unification. The story of the atom is not over. The search continues with boundless curiosity, each discovery opening new questions in the magnificent mystery of the cosmos.